something hurts.
Oh.
I think that's one? Or is it this one? Oh, it's this one.
Okay. So let's do this. Let's do an example of a standard deviation first. We did that last time. I had that one handout we did really quickly. Let's just kind of go through the motions again of how that works. I do have a few calculators. Anybody want to borrow one right now? Yeah. Coming up here with ID. Make sure it turns on before you get too far. Huh? Okay, put that on the desk. Make sure it turns on. Make sure it turns on. Off, or we'll do. Yeah. Uh-oh. Before you put that stuff down, guys, I've only got 2 left. Okay. Yeah, I'll let you use mine. Here, come on. I trust you. Don't make me. Yeah, but you need a great one. All right. So let's do an example. Let's just draw on myself. Let's do an example standard deviation real quick here. Oh, let's see if we can make it come out nice. Come on, okay. That's good. So again, on your formula sheet, you will have the formulas down there. And if I don't say, do you assume that you're working with a sample or a population? Which one? If I don't say. Sample, because what do we almost always work with? Samples. So when in doubt, assume it's a sample. If it's a population, I'm going to have to shout it from the rooftops. I'm going to have to make it, we have the population, I'm going to put it in bold because that's a different situation than we normally have. Is everybody with me? So why does that matter here? For the standard deviation, why does it matter if it's a sample or a population? Why does it matter? What's true about the formulas? If it's a sample, what's the difference in the standard deviation formula? N minus 1 instead of n. So remember, the idea behind a standard deviation is the average distance from the mean to every data point, right? It's the idea behind it. So the formula should have the sum of the distances divided by how many there are, basically, right? That should be what the formula looks like. How do you find the average of anything? Add them up, divided by how many there are. So add up the distances, divided by how many there are would be the average distance. Now on the way we had a couple problems. We had to square it so that it wouldn't add up to be 0, because that sucked, right? We talked a little bit about absolute value being a sucky way to do it. So the population one is this guy. And the standard deviation, that's the variance. And the standard deviation one is same thing except divided by n minus 1. And that was just an adjustment because it's a sample. So it's a population variance, and this is sample variance. All right, let me stop there for a second. We did this. We kind of created those formulas before together. Okay, I like it. Maybe. And again, you can see summing up the distances divided by how many there are. Why is it squared? So that I can kill the negative, so it won't be 0. And why is this one over n minus 1? Because it's an adjustment for it being just a poor little sample. All right, I like it. So believe it or not, every time there's a formula, you should be able to determine what the story behind it is from the formula itself. That's always true, always. Even in weird-ass algebra, it's the same thing. Okay, so what is it? Looking at the formula, what do I need to create? Well, eventually I need to be able to add up those. So I better get a bunch of those so I can add them all up, right? So I'm not going to let you have on your formula sheet like the tops of this stuff or something. How do you determine? Well, you have to make a bunch of those. So what's the first thing I got to do? I got to make x minus the mean, and then I got to square those. So what's the very first thing I have to do then? Because I've got to subtract the mean. I don't even know what the hell the mean is. So how do I get the mean? What do I do? Yeah, add them all up. What's the sum of these? 64.
85.
Yeah. No, it's okay. It's okay. I asked for the sum, but she was one step ahead. So the sum is 85, and then the mean, the mean is going to be, the sum of those divided by n is going to be 85 divided by 5. And that is going to be 17. I like it. Let me stop there for a second. All right. So now I can do 12 minus 17 is? Negative 5, I like it. And again, you could do this in the calculator. We did this on the calculator before. This is not too big of a list, so I could do it a piece at a time. 15 minus 17. 18 minus 17. 9, 10 minus 17. 21 minus 17. And if I add these up, they better be close to at least, or in this case exactly, because they didn't have to round, 0. Right? Sure enough, 4, 2, 6, 7, minus 7, 0. Check. It's a little check I could do. If I had to round, it's going to be close to 0 because I had to round. So if you get negative 17 here, normally it's because somebody tells me the mean of this is 28 or something. How can you very quickly tell the mean ain't 28? Because it's higher than all of your data points. And the mean is supposed to be a measure of the middle, of the center. So how could that possibly be true? So you guys have to get used to stepping out of the work and just looking at it and say, does that make sense, what I just got? If you think the mean is 11 or the mean is 28, there's no way in hell it is. You should be able to catch that kind of mistake quick so you don't keep going. But what I do, thank God you don't have a pretend math teacher who has you do Scantron tests, because that's bullshit. Right? You have a teacher that actually give you partial credit. I'll take points off for that one mistake, and then as long as you do the rest of it correctly conceptually, you won't get any more points lost. Do you guys understand? I won't just keep taking points. Well, that's still wrong, and that's wrong. Of course it's wrong. You made one mistake that threw everything off, and I'm just going to take points off right then. As long as you do the rest of it correctly, you'll be fine. Do you understand? Okay. So now I just have to square these suckers so I don't have this happen. So here I get
4. 25. 4. 1. 4. 16.
That's Lakers fan. So the sum, x minus x bar squared. So now these are a bunch of x minus x bar squares. The formula needs the sum of those. I never put stuff here. That doesn't make any damn sense. I got a whole bunch of those. I'm going to add them up. That whole number goes there. So what do I get when I add these up? 50. Yeah, 20, 5, 50. I like it. So now I can just throw it in the formula and go to town. So the formula says the sum of those, which is 50. Poor little camera. So here I get 50 divided by 4. Why 4? Because how many things are there? 5. And it's a sample, so we're going to have to do 5 minus 1 to adjust for that. I like it, I like it. And this is, again, what does this mean, this S squared? This is the variance. So what's the standard deviation? Take a square root. That's what the symbol's telling me. I haven't taken a square root yet. To kill all those squares I had to do. So square root of 12.5, it's 3 point something. 3.5. 536. So what did you guys get? I gave my calculator away, sorry. And my other calculator's busy.
You said 3 decimal points?
Yes, at least 3 places. Yeah, it's just my quick abbreviation for standard deviation. The symbol in this case is S because it's a sample. If it was a population, it would be this little weird lowercase sigma dude, right? Little fat R.
If it was a top one, would it be 4?
No, any standard deviation, you always take it at least 3 places.
Oh, at least.
Yeah. Later, we're going to talk about probabilities are going to go out to 4 places. So if you just want to take everything out to 4 places, that'll cover your ass for the whole semester just about. All right? It really is me just trying to teach you the idea that rounding too much will hurt you. It's like being 1 degree off in a boat, 8 hours later, you are gone. You're on the island where the lost people were. Weird shit's going to happen to you. I actually never watched Lost, to be honest. I'm fine. All right, so that's the standard deviation. What does that mean? What does that mean? Can you tell me what 3.536 means? It's the average distance that the data points get away from the mean. Right? What's the standard deviation tell you? The average distance that the data points get away from the mean. So if they're all really close to the mean, the standard deviation would be very small. If I was like 2, 7, 80, 914, my God, that's going to be a huge standard deviation, right? Okay, that's what I call hopeful Tai Chi. Okay, like most things here, it's a joke for myself. Let me see. So what else can I ask you here? What if I ask you how many standard deviations from the mean is 19? Does anybody know what the name for that is?
Z-score?
Z-score. But really, all you got to do is like asking you, how many steps away is that desk? Well, how big is every step you're going to take, and how far do you got to go? Same damn thing here. How far do I have to go? How far is the mean from 19? It would be 19 minus, what's the mean? 17. And then I divide it to see how many steps fit in there. I divide it by how big each step is, how big each standard deviation is. So that's the z-score formula, right? Z-score formula is, wow, it's a funky Z. X minus the mean divided by standard deviation. That'll be another little formula we can sit on our formula sheet. So 19 minus 17 divided by? We just figured it out. 3.536. 20 over 35, 4 over 7. It's like 0.57. Sorry. See, my only skill, so I got to show off every night. 0.566 or 0.57. Z-scores will eventually, for right now you can make it 566. We'll eventually round into 2 places because we're going to use a chart to use them that only goes out 2 places. So, but if you put 0.566, you're fine. How are we doing? Everybody decent? You guys all right? No? So again, believe it or not, when I introduce the ideas of what we do in this class, I try to make it make physical sense. If I'm, like 10 feet away from the desk, and every step I take is 2 feet, well, how many steps am I away from it? 5 steps. The distance I got to go divided by how big each step is. That makes physical sense. Because the z-score is measuring how many of these fit in between those. How far apart are they? So would you say 19 and 17 are very far apart? Yeah, how many? It's not even half. It's just a little bit over half a step, right? Not even a full step away. You guys with me? That's what this means. But what if I had a different data set where S was 0.2? Are 19 and 17 very far apart? So it would be 19... Yeah, z-score would be 19 minus 17 divided by 0.2. That is 10. That's 10 steps away. That's really damn far away. So let's the next thing I want to talk about is something that I didn't get a chance to talk about very deeply. So I want to talk about it a little more deep right now, related to what I was just talking about. let me show you why 10 is definitely very far away, while half a step is not very far away. Half a step, I think you'd agree. If you're half a step away from me, I'm like, move over just a bit there, buddy. But if you're 10 steps away from me, that's pretty far away. So let's kind of solidify this idea a bit. Okay. Should we be cool with this here? I mean, this is what I want to see in the homework, and this is definitely what I want to see on the test.
Why do you have 19?
That's just the number I picked. Right here in the question, it was 19.
Okay.
What could I have picked? Any possible data point.
Oh.
Even one that's not there. I could have said, what about 3 if somebody was 3? Came in here, was how far away? That'd be very far away. All right, so here's the idea. And I'm just going to skip to what if I have a normal distribution? What does normal distribution mean again? Bell curve, I love it. Poor little dude. I'm going to fall over. Okay. So if I have a bell curve, here's the interesting thing about it. I know a lot about it. If it was any shape it wanted to be, it could look like any weird shit, right? But if it's a bell curve, there are a few things I know for sure about it. Let me kind of describe a few things. The first thing I know is the mean is the same thing as the median, is the same thing as the mode. Kind of makes sense, because the mean cuts it in half. That's the median, because the median is P50. And that equals the mode, because it's the tallest point on the thing. It's the one that occurs the most. So if I have a normal distribution, this is true. If you are doing the homework, this should have come up at some point in your reading or in the problems. Secondly, probability distribution stuff here. Let's see. Let's talk about how probabilities kind of are distributed. So within one standard deviation of the mean, there is 68% of the data. So if I go down a step, so here's the mean. If I go down one step and up a step, let me introduce this idea. It's a little bit better way to represent those positions. If I use z-scores instead, what is the z-score again? We just talked about a second ago. Yeah, the number of standard deviations from the mean to the data point. So what's the z-score for the mean? 0. So what's the z-score for one standard deviation up from the mean? 1. I just gave it away. It's one standard deviation up, so it's 1. And -1. That's kind of a quicker way to describe within one standard deviation is 1 up and 1 down. So within one standard deviation of the mean, there is 68% of the data. So for example, it's known that men's heights are pretty close to normally distributed. So they look like this. And if you think about it, it makes sense. If I see somebody out here, maybe they're, a dude that's 4'8", would that be kind of like a moment where you're like, well, because you don't see that. Or if I see a dude that's 7'2", wouldn't that be a double take moment? Or no, I don't know. Yes, for most people it would. If you are an athletic trainer working with a basketball team, maybe not, right? But most of us live here. Okay, maybe. So that's going to be 68% of the data right there. So within 2 standard deviations of the mean, so to save myself, there is 95% of the data. So if I go 2 steps away from the mean, it makes sense. 1 step is the average distance from the mean to the data points. 2 steps, I should catch just about all the data. Because on average, they only get the standard deviation away. So 2 standard deviations away, I should catch, and I do. If it's normally distributed, I catch 95%. Even if it wasn't normally distributed, I would catch 75% of the data no matter what, at least that much. And then if I go 3 steps out, I'll catch 99.7% of the data. Holy shit. So 10 steps away is stupid far away. 3 steps away is pretty damn far away. Because think about it. If I was 3 steps away, What percentage is out here? Let me see if you guys can break this down. What percentage is inside here? What percentage is from here to there? I just gave it to you down here. 99.7. So what percentage is just in that side? What percentage is outside? If there's 99.7% inside, there is 0.3% outside. So how much is just on that side? 0.15%. So if your z-score for your height is 3, there's only 0.15% of the population that's taller than you. Whoa. Right? That's pretty up there. Okay, I like it. Jeff is like right here. That's when I realized my basketball dreams were over. When I met my father and he was like an inch shorter than me, that's when I knew my basketball dreams were over. Thanks, Dad. Great chance. This is what's called the empirical rule, by the way. So now you see why I say things about, you can tell, z-scores tell you how far away you are. If I combine it with this, it tells me z-scores that are really freaking far away. In fact, we say that if you have a z-score more than 2 or less than -2, you're unusual. So if anyone had heights that were outside of this region, here or there, they would be unusually short or unusually tall. I like it. So if your z-score in a test was 3.12, what does that mean? What can you tell me? Your z-score for your test grade was 3.12. Are you happy? Hell yeah, you're way above normal, right? So you're way the hell up here. So you're at least in P99.7. I mean, hello. 99.7th percentile? You guys with me? So you're 3.12 steps above the mean. That's what your grade was. Well, you are an unusually high grade, right? Whereas if you're -0.2, well, at least you're not that far below the mean, but you're still below the mean. Not the best place to be, but it could be worse. All right. So these are I need you to understand it well enough so I could say stuff like that and it makes immediate sense, because that's how we talk about data and where it is. I mean, because what's one of the main things statistics does? It tries to see if something is an unusual effect. If I'm trying to prove that my drug works faster than some other drug, I got to show that it works unusually fast compared to the other one. So we're trying to develop a groundwork of where we can define what unusual means. What does it really mean? Well, it means how far away from the average you are. Well, how do you measure distance? Oh shit, z-scores. Okay, all right. So everything's starting to come together, hopefully. Let me think. There was something else I wanted to cover. Any questions about that? I want to do one more thing, I think, from section 2.6. Actually, real quick, before I leave that idea, I do want to do this. So can somebody tell me, don't say anything out loud yet. So this is a normal curve. Can somebody tell me what percentage is in there? So let me remind you guys. What you guys should come in here with a little bit of comfortableness with is somebody giving you a problem that you haven't seen an exact example of, but still able to try something with it. I mean, I don't care that I've never shown you exactly this kind of problem. And you guys are like, well, then you're an asshole. Well, no, you're wrong. I have to push you, especially now that right now I'm not going to grade what you're doing. You can be drawing a duck, is what I like to say, because at least you're doing something. Make me think that you're doing something. But right now is the best time to try something and see if you get it wrong. You can see why you got it wrong, but maybe you get it right. So try to see. Don't say anything out loud yet. Can you figure out what percentage of the data is between there? There's actually several different ways to do it. See, way too many people just staring at me waiting. You have the answer or what? Don't say it. Try something. Do people let you think too enough? Just spoon feed you everything. You have to kind of push yourself a little bit. What do I know? How do I get what I don't know from what I know? Let me give you kind of one way to do this if you think about it. Thanks, Jeff. You put a bunch of dots on the board. Can somebody tell me, I'm going to do it one way and then I'm going to see if anybody did it a different way. Can somebody tell me what percentage this is?
26. 68, yeah.
34%, right? Because what's the mean due to the whole picture cuts it in half. So if there's 68 here, there must be 34 there. So that's 34%. So I've got part of the answer already, don't I? Now I just got to figure out what this is. Can't I do that part the same damn way I just did? What percentage is here? So what percentage is here?
68%.
This is 95. This part will be half of that. Half of 95 is 47.5. So this is 47.5. So how do I get the answer from what I'm asking? I just add them to get the total area. You guys see? There are other ways to do it. Did you do it a different way or did you do it that way?
I went 60 plus 90.
Oh, I like it. So you did 68 plus this little piece. I love it. Okay, that's another way. So do you see how every way you can do it is basically dividing the area I want up into parts I can manage? So here, what do I get? 81.5? All right. So that kind of problem is not even the stats problem, to be honest. I didn't have to draw this picture. I could have done the same numbers with somebody and just put it on a board. It's just using the numbers you know correctly. That's all that is. And that's actually a huge part of statistics is the area of stuff and just being able to subtract some areas off and add areas together when you're supposed to. Okay. All right, so here's the last idea for today. And I'll let you guys out a little tiny bit early.
Gee, thanks, Jeff.
Sure. So everybody got what they want here? More than you ever wanted? Okay. Last thing, section 2.6. If you have not done the homework yet, requires some reading. I do that every now and again to you guys to remind you that you have a book for a reason, right? There's the idea of skewed, not screwed, skewed. Skewed left and skewed right. So if I have a normal curve, skewed left would be like somebody takes it and pulls it to the left. So it becomes what I call a Java curve, right? Oh, let's see. It's my horrible Java. Java the Hutt? No?
Yep.
All right, I'll stop. Skewed left, I pulled it to the left. Skewed right, remarkably enough. Make this even more pronounced for you guys who've got it. So I pull it to the right like now. So if I gave you like a histogram, this is skewed what?
Right.
Skewed right.
Right.
Somebody took it and pulled it this way. Stretched it that way. Basically, it's the direction that the tail is going in. That's why I like to think it's Java in his tail. No? Oh, geez, don't say that. Don't ever say that to a nerd. Did Luke homework win the Force? It's one of my favorite comedians. All right. And let me see, what else is in there? There was, there's symmetric. I mean, the uniform distribution is, uniform. The normal distribution is symmetric. It looks the same on the left and the right. So these are obviously not symmetric. These are off from symmetry somehow. So would you say that, this is symmetric? Sure, it's not perfect, but this is definitely close enough to symmetric to say that's symmetric. I like it. You guys with me? A little bit? Doesn't have to be perfect. You could say it's close enough to symmetric, or it's definitely closer than, Is that symmetric?
No.
Oh, hell no. It doesn't come back down, so screw it. I like it.
So, what would that be?
Yeah, what would this be? It looks like it's skewed left in a way, right? It's even like, it's more pronounced than this. It's like the bump is like right at the beginning and then you go, wow. So this one the other way is like, wow. So yeah, it's still skewed left. Okay, I like it. Anybody make it into section 2.6 homework yet? You guys are like, I like that reaction. Okay, it's possible it could happen. Man, you guys are very happy that I pushed the test back. What's that? Oh, you asked me a question now. Okay. All right, guys, so you can try this or not. It's up to you. I'll have the answer key for it Wednesday.
So you took away the points because of didn't finish.
Can you put them back in the bag?
Because I didn't finish my words.
Sorry?
I took away the points because I didn't finish my words, or
I got to remember. All affected workers. Oh, yeah. No. What's the key thing? Where are they? Brazil. Brazil.
yeah.
Otherwise, all the factory workers that are around the whole world? No, just Brazil. That's they focused on
I
that.
gave you my other homework earlier, but this is the corrected one. I gave you the corrected one, so I had a mistake on right.
Yes.
So I gave it to you
Earlier.
earlier.
Up here? Up here. In here?
Oh no, I handed it to you.
Oh, you handed it to me, so I probably put it here. No? So maybe it's in my book. You mean earlier today?
Yes.
Okay. Where did I put you then? Maybe it is. What's up?
Can I turn this in now, or do you want to wait till the test?
I appreciate it,
For
brother.
the
Man.
correction.
Oh, you can turn this in. There you
There.
are. Jeez. All right. So let me put corrections. Okay, cool.
I had a question right here.
Yeah.
So this is cluster basically.